Category O, lecture number 13, Kazhdan-Lusztig conjectures. Let us start with recalling the graded setup for category O. Let us fix a dominant weight lambda. So here dominant means with respect to the integral Weyl group of this weight. And let W prime be the dot stabilizer of lambda. W prime is a parabolic subgroup of W lambda. Then we have the associated indecomposable block of category O, which we denote O lambda. So this is the indecomposable block, which contains the simple highest weight module L lambda. This block has a unique indecomposable projective-injective module, namely the module P W0 upper lambda dot lambda. So this projective module is also injective. Consider the coinvariant algebra of W lambda, which we denote by C lambda. This is naturally a Z-graded algebra. And then in this algebra, we can consider the subalgebra of W prime invariants, denoted C lambda upper W prime. Zergel's combinatorial description of O lambda asserts the following. The endomorphism algebra of the indecomposable projective-injective module PW0 dot lambda is isomorphic to the algebra of W prime invariants in C lambda. Furthermore, the functor of taking homomorphisms from this indecomposable projective-injective module is full and faithful on projective modules in O lambda. And for any indecomposable projective module PW in O lambda, the image of this module PW under this functor is a Z-graded module over the algebra C lambda upper W prime. Therefore, if we take P lambda, some basic projective generator of O lambda, we have the following consequence, that its endomorphism algebra, which we denote by A lambda, is naturally a Z-graded algebra. So in this case, we can consider the category of all finite-dimensional Z-graded A lambda modules, which we denote by O lambda upper Z, and this is a graded version of the block O lambda. Morphisms in this category are homogeneous homomorphisms between A lambda modules, which have degree 0. Let us now talk about the graded Grothendieck group. We denote by 1 in angular brackets the endofunctor of the category of graded A lambda modules of the category O lambda Z, which shifts the grading by 1. And our convention is that this endofunctor maps elements of degree 0 to elements of degree -1. Of course, it's an autoequivalence of this category, and it generates a free action of the additive group of integers on this category, and this is a free action by autoequivalences. So let us now consider the usual Grothendieck group of this category. Of course, the free Z action on O lambda Z induces a free Z action on this Grothendieck group. Therefore, we can consider this Grothendieck group as a module over the Laurent polynomial ring with integer coefficients and in one variable v, under the convention that multiplication with v inverse corresponds to our graded shift 1 in angular brackets. Let us now discuss what kind of modules in the usual category O have graded lifts. Of course, we have the functor from O lambda Z to O lambda, so from the graded version of O to category O, which just forgets the grading. However, a warning is that this functor is not dense. In the general case, there might be some modules which are not gradable, which do not admit graded lifts. So the definition, a module is gradable if it is isomorphic to a module lying in the image of this forgetful functor. and usually the corresponding preimage is called the graded lift of the module. A standard fact is that an indecomposable module, provided that it is gradable, admits a unique graded lift. Of course, unique up to something, unique up to isomorphism and shift of grading. So what we know directly from the definition that all indecomposable projective modules are gradable. The claim is that all Verma modules are gradable. Proof: the Verma module delta W is defined as the quotient of the indecomposable projective PW by the trace in this projective of all indecomposable projectives Px such that x is brüha smaller than W. Since both PW and Px are gradable modules, the trace is a gradable module, because the ungraded space of all homomorphisms from Px to Pw is, by definition, because these two are gradable modules, it's a direct sum of homogeneous components. Therefore, we can take the corresponding homogeneous homomorphisms, adjust Px by shift of grading, and then we obtain that the trace, which is the sum of the images of all such maps, is a graded submodule of Pw. So this is for an individual x, and you can do it for all x which are brüha smaller than W. So therefore, since the trace is a gradable module, the quotient, which is delta W, is also a gradable module. So all Verma modules are gradable. Our next observation is that all simple modules in O lambda are also gradable. The proof is quite similar. We note that the simple module LW is a quotient of the Verma module delta W by the trace in this Verma module of all projective modules Px such that x is now brüha greater than W. Again, since delta W is gradable from the previous slide and all indecomposable projectives are gradable, the trace is gradable. And hence the quotient, which is the simple module LW, is also gradable. So let us recall that our projective generator P lambda is basic, so it's multiplicity free, and hence our algebra A lambda is basic. So this means that all simple A lambda modules are one-dimensional. So if we have graded one-dimensional modules, they must be concentrated in a single degree. This leads to the following standard graded conventions. So assume that W is an element in W lambda. We denote by LW the graded simple module corresponding to W, which is concentrated in degree 0. Then PW is the indecomposable graded projective cover of LW. So the top of PW is concentrated in degree 0. Further, IW is the indecomposable graded injective envelope of LW, so the socle of IW is in degree 0. Delta W is the graded standard quotient of PW, so this is a graded version of the Verma module, where the top is concentrated in degree 0. And similarly, nabla W is the graded version of the costandard module, where the socle is in the degree 0. One should note that indecomposable projectives in the graded category O are, up to isomorphism, the modules PW and then with the gradient shifted by K, so where W is an element from W lambda and K is an integer. And similarly, all other structural modules, the simples, injectives, standards, and costandards, can be obtained from these standard graded modules using the shift of grading. So let us recall the Heke algebra, which we discussed in the previous lecture. So the Heke algebra is the associative algebra over the ring of Laurent polynomials with integer coefficients in the variable v, and it is generated by symbols hs, where s is a simple reflection, subject to the following relations. So we have the quadratic relation hs plus v times hs minus v inverse is equal to 0, and the usual braid relations. So we have the standard basis of this algebra, which is constructed as follows. If W is an element in the while group with a fixed reduced expression, then we define HW as the product of HS1, HS2, and so on, HSK, following the reduced expression S1, S2, Sk of W. The Heke algebra has a bar involution, which is defined by V bar is equal to V inverse and HS bar is equal to HS inverse. So this is a unique automorphism of the Heke algebra, which has these two properties. And HS bar is equal to HS inverse should be valid for all simple reflections S. And as we discussed, the Heke algebra H has a Kazhdan-Lusztig basis. That is, for any element in W, there is a unique element HW underline in H, which is self-dual with respect to the bar involution, and which can be written as the sum of HW of the standard basis element plus the linear combination of all standard basis elements with coefficients given by polynomials in V without constant term. And Kazhdan-Lusztig polynomials are defined as entries in the transformation matrix from the standard basis to the Kazhdan-Lusztig basis. The algebra H has also the symmetrizing trace form tau with values in the Laurent polynomial algebra with integral coefficients in V, which is defined by taking the coefficient at the identity element with respect to the standard basis. So using this symmetrizing trace form, we can define the dual Kazhdan-Lusztig basis, which consists of elements HW underline hat. And this is uniquely given by the property that tau of hx underline times hy inverse underline hat is equal to the Kronecker delta x y. So now we are ready to formulate what is known as Kazhdan-Lusztig conjectures. So observation, there is a unique isomorphism of A algebras from the Grothendieck group of the graded version of category O to the Heke algebra, which sends the class of the standard module delta W to the standard basis element HW for W in W. So why is that? So this is because we know that the classes of Fermat modules form a basis in the ungraded Grothendieck group, and the fact that this is a homomorphism of A algebras takes care of the grading. So our A algebras, Laurent's polynomials in V, we have interpreted the action of V on the graded Grothendieck group as the shift of grading. So the classical Kazhdan-Lusztig conjectures from 1979 assert the following. So we assume that lambda is regular. Then, under this isomorphism, the classes of indecomposable projectives are sent to the corresponding elements in the Kazhdan-Lusztig basis, and the classes of simple modules are sent to the corresponding elements in the dual Kazhdan-Lusztig basis. It is very easy to see that one of these claims, taken for all W's, implies the other one. So if one wants to prove this, one wants to prove only one of these two claims. So the literature, the original conjecture was formulated in the paper Representations of Coxeter groups and Heke algebras by Kazhdan and Lusztig, which was published in Invenciones in 1979. It was proved quite fast. There were two original proofs, one of them by Beilinson and Bernstein in 1981, and another one by Brylinski and Kashiwara, also in 1981. Fairly recently, in 2014, Elias and Williamson provided a purely algebraic proof of this conjecture. So let's consider the SL2 example. So if G is the Lie algebra SL2, then the corresponding Weil group has two elements, the identity and the simple reflection S. And the corresponding Kazhdan-Lusztig basis is quite easy. The Kazhdan-Lusztig element for the identity is just the identity, and the Kazhdan-Lusztig basis element for S is equal to HS plus V HE. The principal block of category O has simple modules L0 and L-2, so in our notation L0 is LE and L-2 is LS. And the graded Löwy filtrations of projectives are as follows. So this is a degree 0 layer, so the indecomposable projective PE has top E in degree 0 and socle S in degree 1, and the indecomposable projective PS has top S in degree 0, then E in the middle in degree 1, and the socle S in degree 2. And both these projectives have Fermat flags, so PE is a Fermat module, just delta E, and PS has Fermat module delta S on top in degree 0, and Fermat module delta E shifted by -1, so starts with top in degree 1. And we can now compare it to the Kazhdan-Lusztig basis, so HE is just HE, so it's just one Fermat module, while HS underlined is HS plus VHE, so it has the Fermat module S in degree 0 plus the Fermat module E starting in degree 1, exactly as on the picture. And similarly, the composition multiplicities of simples in Fermat modules, they can be obtained using the Bich-G reciprocity. We see that delta E has identity in degree 0, so this corresponds to this HS, and S in degree 1, so this corresponds to this VHE, and delta S has just S in degree 1, so this corresponds to this HE. So what does one need to prove in order if one wants to prove Kazhdan-Lusztig conjecture? Recall that we have the mu function, which we defined in the following way. So if you have two elements x and y, which are not related in the Brugha order, the mu function is 0. And if they are related in the Brugha order, the mu function is defined in the symmetric way, mu of xy is equal to mu of yx, and it is defined as the sum of the coefficients at linear terms of the Kazhdan-Lusztig polynomials hxy and hyx. So the mu function is important in the induction step when we construct the Kazhdan-Lusztig basis. So if we take the Kazhdan-Lusztig basis element HW underline and try to multiply it with the Kazhdan-Lusztig basis element HS underlined, in the situation where WS is Brugha greater than W, the outcome will have the following form. It will be HWS underlined plus the linear combination of Kazhdan-Lusztig elements HX underlined, where X is Brugha smaller than W and satisfies the property that X is Brugha bigger than XS. And the coefficient in this expression is given exactly by the mu function mu xw. If we accept Kazhdan-Lusztig conjecture, it means that elements of the Kazhdan-Lusztig basis correspond to indecomposable projective functors on category O. So this equality, translated into the language of indecomposable projective functors, gives us the following equality: that the composition of theta s and theta w is theta ws plus the direct sum of theta x's with the same conditions and with the multiplicity given by the mu function. Now, if we evaluate this isomorphism of functors at the dominant Fermat module, we get the following: that applying the indecomposable projective functor theta s to the indecomposable projective module PW, we get PWS plus the direct sum of PX's with multiplicities given by the mu function. Please note that this is a graded statement. We work in the Heke algebra, so this is the statement about graded modules, despite of the fact that there are no graded shifts appearing in this picture. So the statement is that we have such a decomposition without any graded shifts. But this is a graded statement. If one wants to prove Kazhdan-Lusztig conjecture, one needs to prove this formula for the action of the translations through the wall theta s on an indecomposable projective Pw under the assumptions that Ws is greater than W. So this is what one needs to prove. So let us now discuss graded combinatorics of translations through walls. So consider the coinvariant algebra C and a simple reflection S. Then we have the corresponding subalgebra CS of S invariance in C. It is very easy to see that C is free over CS of rank 2. Moreover, the basis of C as a module over CS can be chosen to live in degrees 0 and 2. Consequently, if we take the composition of the induction from CS to C, followed by the restriction from C to CS, this composition is isomorphic to the identity functor on CS plus the graded shift of the identity functor on CS shifted by -2. So this is because of this degree 2 appearing here. And using Sergel's combinatorial description of translation functors, we thus get that the composition of theta s with itself is isomorphic to theta s shifted by 1 in the grading plus theta s shifted by -1 in the grading. So this is a consequence of this and how the grading is adjusted for the functors theta s. And it's a nice exercise to check that this is a correct adjustment of the grade. So in particular, from this it follows that if we have an element W in W such that Ws is Brucha smaller than W, then the composition of theta S and theta W is isomorphic to the direct sum of theta W shifted by 1 and theta W shifted by -1 in the grading. Again, evaluating at the dominant Verma module, we get that theta S applied to Pw is Pw shifted by 1 plus Pw shifted by -1. And how we prove this? We take a reduced expression of W which ends with S, and then use the fact that theta S squared is theta S shifted by 1 plus theta S shifted by -1. So let's now discuss the combinatorics of graded translations of Verma modules through walls. So we know that the Kazhdan-Lusztig element corresponding to S is HS plus V HE. Hence, for any element W in W, we have the following formula, which was crucial in our proof of the existence of Kazhdan-Lusztig basis. So if we multiply the standard basis element HW with the Kazhdan-Lusztig basis element HS underlined, we will have HWS plus VHW in the case WS is longer than W, or HWS plus V inverse HW in the case WS is shorter than W. Recall that for W in W, we have the following short exact sequences. So if W is shorter than WS, then the Verma module delta W is a submodule of theta S applied to delta W with the cokernel given by delta WS. So if WS is Brucha smaller than W or just shorter than W, then delta WS is a submodule of theta S delta W, and the corresponding cokernel is given by delta W. Consider the decomposition theta S applied to the indecomposable projective injective Pw0 isomorphic to Pw0 shifted by 1 plus Pw0 shifted by -1. This was discussed on the previous slide. From this decomposition, it follows that if we apply theta S to Lw0, we will get Lw0 in degrees 1 and -1, and no other occurrences of LW0 in this module up to shift, of course. So since LW0 is the socle of any Verma module and has multiplicity 1 in this Verma module, it follows that the graded version of these short exact sequences has the following form. So if WS is longer than W, then delta W shifted by -1 is a submodule of theta S delta W, and the quotient is delta WS. In the case WS is shorter than W, delta WS is a submodule of theta S delta W, and the corresponding quotient is delta W shifted by 1. And now this graded picture should be compared with this formula in the Heke algebra. So we apply theta S to delta W, and we get delta WS, always without shift, and then we get delta W shifted by 1 or -1, depending on whether WS is shorter or longer than W. In this way, we have the perfect match between these formulas in the Heke algebra and the short exact sequences which we have in category O. The combinatorics of graded translations through walls of Verma modules allows us to describe combinatorics of graded translations through walls of simple modules. So let W be an element in the while group such that WS is longer than W. Then from the BGG theorem, we have the inclusion of Verma modules. Delta WS is a submodule of delta W. Moreover, we know that theta S applied to delta W is isomorphic to theta S applied to delta WS. From this it follows that theta S applied to LW, so LW belongs to the quotient of delta W by delta WS. This must be killed by theta S. So under the assumption WS is longer than W, theta S applied to LW is 0. In the case when WS is shorter than W, we have the natural surjection of theta S delta W onto theta S LW, given by applying the exact functor theta S to the natural surjection of delta W onto LW. And from the previous slide, we have the short exact sequence delta WS is a submodule of theta S delta W, and the quotient is delta W shifted by 1. Similarly, in the same case when WS is shorter than W, we have the natural inclusion of theta S LW into the theta S translation of the dual Verma module nabla W, and we have a similar short exact sequence, nabla W shifted by -1 is a submodule of theta S nabla W, and this is projected then onto nabla WS. So combining these two facts together, we see that theta S LW has a copy of LW which lives in degree 1. One copy lives in degree 1 coming from here, and another one lives in degree -1 coming from here. And there are no other appearances of LW in this translation up to graded shift. Also, we can readily see from these pictures that the subquotient LW, which lives in degree -1, is the simple top of this module, of this translated module, and the subquotient FW, which lives in degree 1, so LW shifted by -1, is the simple socle of this translated module. So this allows us to define the Janssen middle. So for an element W in W and a simple reflection S such that WS is shorter than W, the Janssen middle JWS is defined as a quotient of the radical of the translated module theta SLW by the socle of this translated module. The claim is that for any element x in W such that x is shorter than xs, we have that the dimension of the homomorphism space in category O from the Janssen middle to Lx is equal to the dimension of the homomorphism space in the opposite direction, and this is also equal to the dimension of the x1 space between Lx and W in both directions. First, we know that the claim that the last two dimensions coincide follows directly using the simple preserving duality. So it's contravariant, so it changes the direction of the x, and it is simple preserving, so it just swaps the x1 from Lx to Lw to the x1 from Lw to Lx. Furthermore, given a short exact sequence Lx submodule of M with quotient Lw, we have that applying theta s to M, we get the same module as to apply theta s to Lw. So this is because theta s kills Lx, because xs is shorter than x. So by adjunction, we then can compute that hom in category O from theta sm to M is equal to hom in category O from theta slw to M. This is because theta sm is the theta slw. Now we can move theta s around by adjunction, so this is equal to hom from Lw to theta sm, and again we can substitute theta sm by theta slw. So this is equal to hom from Lw to theta slw, and we know this is one-dimensional. So this implies that any module M can be found as a quotient of theta slw. In other words, that the homomorphisms from the Janssen middle, so the corresponding Lx should appear in the top of the Janssen middle. So the homomorphisms from the Janssen middle to Lx, this space should be isomorphic to the space of the first extensions from Lw to Lx. And the second claim that we can also swap the two arguments here, it is proved similar. What exactly does one need to prove for simple modules in order to establish Kazhdan-Lusztig conjecture? So the point is that the Kazhdan-Lusztig conjecture is equivalent to the claim that for any W in W and any simple reflection S such that Ws is shorter than W, the corresponding Janssen middle module JWS is semi-simple. So here is an explanation why this is true. So if we assume the Kazhdan-Lusztig conjecture, then we already know that the theta s squared is equal to theta s plus theta s. So if we evaluate it at Lw, we readily see that this implies that theta s kills the Janssen middle. So any subquotient of Janssen middle must be Lx, where xs is longer than x. So we have the standard notation where hom and x starting with a small letter means homomorphisms and extensions which are homogeneous of degree 0. So by adjunction, for any integer I, the space of these small homomorphisms from Px shifted by I to the Janssen middle is equal to the space of homomorphisms from Px shifted by I to theta s Lw, and now we can move theta s by adjunction, so this is hom from theta s Px I to Lw. And theta x Px, so we already discussed that Kazhdan-Lusztig conjecture means this formula, theta s Px is isomorphic to Pxs plus the direct sum of Py's under some conditions with the multiplicity given by the mu function, right? And no graded shifts. So in particular, since no graded shifts appear in this formula, this homomorphism space can be non-zero only if I is equal to 0. But this means that Janssen middle must be concentrated in a single degree. And later on, we will see that Kazhdan-Lusztig conjecture means that all modules concentrated in a single degree are semi-simple. So let us now discuss some consequences from Kazhdan-Lusztig conjectures. The first consequence we already mentioned several times. So if we have an element W in W and a simple reflection S, then the composition of theta S and theta W, under the assumption that Ws is shorter than W, is isomorphic to theta W shifted by 1 and theta W shifted by -1. And we have exactly the same formula for the multiplication theta W and theta S in case SW is shorter than W. In the other case, where Ws is longer than W, then theta S times theta W is isomorphic to theta ws plus the direct sum of theta x's with the assumptions that x is shorter than w and xs is shorter than x, and we have theta x with a multiplicity given by the mu function. And we have a similar formula if we swap the order of the product, and here we swap the conditions that SW should be no longer than W. And this follows directly from the induction step in the proof of existence of Kazhdan-Lusztig basis, since we know that theta W should be matched by Kazhdan-Lusztig conjecture with the Kazhdan-Lusztig basis element HW underlined under the isomorphism between the graded Grothendieck group and the Heke algebra. Please also note that from Kazhdan-Lusztig conjecture, it follows that all Kazhdan-Lusztig polynomials have non-negative coefficients because those coefficients describe certain multiplicities of some modules in some other modules. So they describe graded multiplicities of Vermas in Verma flags of projective modules. The second consequence of Kazhdan-Lusztig conjecture is positivity of the grading. Consider a basic projective generator P lambda of O lambda. Assume that we normalize the shifts of indecomposable summands of this projective generator such that all graded modules which appear in it have top concentrated in degree 0. Then we have that the endomorphism algebra of this module is Z-graded, and we claim that the grading on this algebra is then positive in the sense that all non-zero components are concentrated in non-negative degrees, and the degree 0 part is semi-simple. So to argue for this, we know that all Kazhdan-Lusztig polynomials are genuine polynomials in V, and any Verma module appearing in the Fermat filtration of PW thus satisfies the condition that this Verma module should be shifted in the non-negative direction in the gradient. So in particular, it has top in a non-negative degree. And from the BGG reciprocity, it follows that each simple appearing in a Verma module also lives in non-negative degrees. And the only things which can be in degree 0, so for PW, it's only delta W, which has top in degree 0, and it appears once. Everything else is properly shifted because all non-trivial Kazhdan-Lusztig polynomials are polynomials in V without constant term. So in particular, it follows that each indecomposable projective has top in degree 0 and all other simples in strictly positive degrees, which implies exactly that the basic algebra A lambda describing category O is positively graded. So consequence number 3 is the information which Kazhdan-Lusztig conjecture gives about the quiver of the algebra describing category O. So denoted by lambda, the quiver of O lambda. So this is the Gabriel quiver, the oriented graph where vertices are simple modules and the number of directed arrows from one vertex to another is the dimension of the X1 space between the corresponding simple modules. So the vertices of lambda are naturally identified with the Weil group, and the existence of the simple preserving duality actually implies that the number of arrows from X to Y always equals the number of arrows from Y to X. So we have the standard arrows, so given X and Y, such that the lengths of X and the lengths of Y are different by 1, then there is exactly one arrow from Y to X, which corresponds to the inclusion of Verma modules delta Y and delta X, provided that such inclusion exists. So if Y is Bruchá longer than X, and the difference in their lengths is 1, then we have one arrow between Y and X, which corresponds to this inclusion. But we also have additional arrows which are given by the mu function, and they correspond to the extensions which are described by Janssen middles. Given two elements X and Y, such that X is Bruchá smaller than Y, the claim is that there are mu xy arrows from X to Y. They correspond exactly to the situation which was described here in this proposition for Janssen middle. Please note that for big Coxeter groups, or for big Weil groups, the values of the mu function can be arbitrarily large. So the quiver of category O gets bigger and bigger. And for singular blocks, the quiver can be obtained by translating certain parts of the quiver for the regular blocks to the wall. For more details about the quiver of category O and for a certain algorithm how to compute it, we refer to Wybornow's paper Perverse Sheaves, COSUL, IC modules and the quiver for category O from 2007. Let's do an SL3 example. This is an easy example where mu function is quite trivial. So in the case of SL3, the Weil group is the group S3. It consists of E, ST, ST, TS, and W0, which is STS and TST. So one can compute the following graded filtrations of projectives in category O. So the projective PE is just the Verma module, SL3 is multiplicity 1 case, and the layers of the Verma module follow just the lengths of the elements in the Weil. The projective module PS has two Verma modules in its Verma flag, the Verma delta S and delta E shifted by 1. Similarly, PT has delta T on top and delta E shifted by 1. PST has delta ST on top, delta T and delta S shifted by 1, and delta E shifted by 2. Similarly for TS. And finally, PW0 has delta W0 on top, delta ST and delta TS shifted by 1, delta T and delta S by 2, and delta E by 3. So the quiver of the principal block of category O is just a doubling of the Hesse diagram of the Brugha order on S3. So each arrow in the Hesse diagram is doubled by an arrow going in both directions. So the number of arrows between any pair of elements in the quiver is the same in each direction because of simple preserving duality. And the mu function is trivial. All multiplicities are given by the elementary relations in the Brugha order. So this is a quiver of the principal block of category O for SL3. The smallest example where the mu function starts playing a non-trivial role and where the Kazhdan-Lusztig polynomials gets non-trivial is the example of SL4. If we denote the simple reflections for SL4 as R, S, and T, and the Dynkin diagram is as here, then here is a list of non-trivial Kazhdan-Lusztig polynomials for this group. So the Kazhdan-Lusztig polynomial from S to SRTS is V plus V to the power 3. So it's not a monomial polynomial, and we see here that we will have a non-trivial mu function. The degree 1 coefficient here is non-trivial. So this implies also that we have a non-trivial Kazhdan-Lusztig polynomial from E to SRTS, which is V squared plus V to the power 4. The second instance of non-trivial Kazhdan-Lusztig polynomial is the one from RT to RSTSR, and this is equal to V plus V to the power 3. Again, the non-trivial mu function here, the linear term is non-zero. And this leads to three other Kazhdan-Lusztig polynomials, so we can manipulate the first thing for R, T, and E. We can go to in the Brugha order, make elements smaller for this thing. And we have the corresponding non-trivial Kazhdan-Lusztig polynomials. So we have two non-trivial values of the mu function and the non-trivial subquotients of the dominant Verma modules, which correspond to these two non-trivial polynomials. So delta E has a subquotient L SRTS, which appears in degree 2. The expected subquotient, which is given by inclusion of Verma modules, should be in the degree given by the length, so it should be in degree 4. And similarly, delta E has an unexpected simple module, which corresponds to RSTSR and lives in degree 3. The expected module for this element lives in degree 5. This corresponds to these polynomials v squared plus v4 for SRTS and v cubed plus v5 to the power 5 for RSTSR. It's interesting to observe that these two elements SRTS and RSTSR are exactly the involutions in S4 which are not longest elements in parabolic subgroups. So these involutions which are not longest elements in the parabolic subgroups are always trouble. Somehow this is the upshot of this example. So let's finish with some questions for PhD students. Question number 1, so give a full proof for the claim that graded lifts of indecomposable modules, if exists, are unique up to isomorphism and shift of grading. Question number 2, check that the graded shifts in this formula, theta x composition with theta x, is theta x shifted by 1 plus theta x shifted by minus 1 are correct. Question 3, prove that Janssen middle is self-dual without using the Kazhdan-Lusztig conjecture. Question number 4, prove that semi-simplicity of Janssen's middle implies Kazhdan-Lusztig conjecture. Question number 5, compute all Kazhdan-Lusztig polynomials in type G2. Thank you very much. See you next time.